Okay, hello and welcome to my channel. Today we're gonna talk about the three claims that would back up the non-degeneracy of 1D bound states. So let's get started with the first one is that for any 1D bound 1D potential that spans over X, the bound states are non-degenerate, at least for normalizable energy eigenstates. So, should I write it? Probably. So no degeneracy in 1D bound state. For any potential that spans X, so that is X from minus to plus infinity with normalizable. So these are, that is your first statement. Now we move on to the second one. So with any potential that is real, the energy eigenstates can be chosen to be real as well. And the bound states are real up to a phase. And we will see that in this sort of proof here. The second one is that with real potential, it can be real. These be real up to a phase. So here is your claim, and to back it up, we're gonna take a look at the proof here. So proof. So example, you're given these two, the real, the imaginary, right? Or the real is real plus the real minus imaginary. No, what was it again? Real plus. Okay, no. I got this messed up. It is plus the complex conjugate over 2. This is minus the conjugate over 2i, I believe it is. All right. So with this, now we take a look back at the first claim that there are no degenerate bound states. So we can conclude that imaginary gotta be a CR. So it cannot be the same, it's gonna be sort of different here. So now you can write, as you know, your wave function is a complex function. So it is R plus I psi imaginary. From here, you can expand this as plus ICR. There you go. Now you got this. You can sort of factor out the psi r. So that is 1 plus IC psi r. You do this, and you see you can polarize this one, and you would get something that is, well, an exponential I argument of 1 plus IC, the root of 1, sorry, 1 plus C squared psi r. And since your E here is a global phase, so it doesn't really matter, and your wave function is still real. Right, so that is basically the proof for the second claim. Now we move on to the third claim. The third claim is that if your potential is symmetrical, meaning that your V of x is equal to the V of minus x, the energy eigenstate can be chosen to be either odd or even under the movement that you moved from x to minus x. And for 1D potential, the bound states are always either odd or even. So that is a lot of words. Would write that down and provide proof. So maybe I would have to erase these. Third one. So I will just write it briefly. Just bound states are either odd, even, or x equal. Yeah, right. So there are actually two ways you can view the proof of this. First one is that you will use the parity operator, which is the way that I find kind of more mathematics. And another way that you would just define your side of minus x, which would be a bit easier to imagine. So I would just start with the one with parity first. So there are actually two ways that I know of. Just classify that. So the first one is that you would utilize the parity operator. So the definition of parity operator is that if you apply it twice on something, you would get that same thing. So from here, you can sort of split this guy into odd and even. So with even and odd, you apply your parity operator. This would give you plus psi of plus. Okay, that is, this one is psi of minus. That is the parity operator there. Now let's take a look at your, well, time independent Schrodinger equation. So this one would actually be used for both of the way to prove this. Yeah. So take a look at this guy, and when you act the parity operator on this, it doesn't change. First one here, since this is the second derivative respective to x, you would just get 1 back. So it doesn't change this. And for the potential, it doesn't change that as well, since you got that v of x is equal to v of minus x. All right, so once you got that, you can see that this guy is the Hamiltonian. And as I said, this parity operator on this doesn't change it, and parity operator on v of x doesn't change it, since we have this guy to protect that, and for this part is the x squared that protect this part. So from that we can say the Hamiltonian commutes with the parity operator. And if you remember, I think I have mentioned this before in the the commutation of operator video, so you can maybe look back on that thing. Right, so when you have this, meaning that when you act your parity operator on the time-independent Schrodinger equation. So meaning that if you got this, the order here doesn't really matter anymore, meaning that you can move your parity operator straight into the wave function. So you can just act on the wave function with the parity guy first. And since here it's a number, so you can just move it. Group that. So that means that either your psi or your parity, no, but gotta be a way to read this. Your pi on psi are both solution for your Schrodinger equation. It means that you can split, and you first gonna define the odd and even guys. So just define it somewhere here. Oh, yeah, x and minus x. This guy is x plus minus x over 2. That guy is x minus a of minus x over 2. There we go. You got that. And you got this over here as well. Therefore, you can get that, well, your odd wave, your even wave function, sorry, going to be equal to your odd wave function. And remember the first claim, you're going to put a C there. Okay, now you can apply a parity operator on here again. That would yield you psi of psi even is equal to C squared psi odd. And from here, you get that this is equal, okay, you would get that is plus C minus and psi minus C plus. Therefore, your C can only be plus minus 1. And there we go. It has to be either odd or even. So that is the first way that you can prove this. There is another way that is maybe more imaginable. And you don't have to know all these operator stuff. Alright, so the second way is that you would define your psi of minus x. So first let's just pull all these over here to get do a bit of rearrangement. 2m h bar minus v x that's 0. Right, so here this act on this would just be that plus that is equal to 0. That is psi of x. Now what you would want to do here is you would define another function that is psi of minus x. So we're gonna define, say, phi of x is equal to psi of minus x. And you do double derivative on this guy. Well, the first derivative would give you minus and derivative. Then the second derivative would remove that would remove that minus sign. So that guy would just be like so. No more minus. Okay, maybe psi. Yeah. Right. So you can take a look at that. So if you sub in phi of x instead of psi of x for your time-independent Schrodinger equation, it would actually just be the same. So you would only get this thing when you evaluate it at phi minus x. This is minus x, I'm sorry. So when you move this to minus x, you would get the same thing. Move this, which is the same, so I'm just not going to change it. Yeah. So you can see that this guy is the same as your phi. So you got this. You can say that both your psi of minus x and psi of x is the solution for your Schrodinger equation here. Now we're gonna do as we did for the first one, is that you define these odd and even wave function. There we go. You do that, and since this is a 1D potential, a 1D system, your wave function doesn't really rotate. Therefore, it doesn't have that imaginary number part. So you can get that your psi is psi is real. There we go. Your psi is real. So that this, okay, so from these, you get that just as we did before, these would have to equal to a constant times the opposite. There we go. And this is what you got. And from here, you can get that c squared is equal to 1. Therefore, your c is equal to plus minus 1. And that is the proof for the third claim. So yeah, that is it. Goodbye.